Welcome back to G Fun Facts Online. Today, we are shifting our gaze from the launch pad to the landing zone. The red dust of the South Australian outback has barely settled, but the impact of what happened yesterday at the Cooniba test range is already sending shockwaves through the aerospace industry. When Varda Space Industries W-5 capsule streaked across the sky and touched down on January 29, 2026, it did not just deliver a payload of space-manufactured pharmaceuticals. It delivered a message. That message, written in the charred ablative crust of its heat shield, is that the era of bespoke reentry is over. The age of mass-producible, industrial-grade return from orbit has begun. For decades, the conversation about the space economy has been dominated by a single vector: launch. We have obsessed over dollars per kilogram to orbit, celebrating every reusable booster landing and every drop in the price of a Falcon 9 flight. But launch is only half the equation. If we are to build a true orbital economy, one where we do not just visit space, but work there, build there, and bring value back, we need to solve the problem of getting home. We need a way to bring goods back from orbit that does not cost a fortune, does not require a national-scale engineering effort for every mission, and does not rely on technology frozen in the Apollo era. Enter the C-PICA shield. The technology that protected the W-5 capsule, and which is now poised to protect a fleet of commercial spacecraft from Varda, Inversion Space, and others, is a material known as Conformal Phenolic Impregnated Carbon Ablator, or C-PICA. It is an innovation that might lack the visceral roar of a Raptor engine, or the sci-fi silhouette of a starship, but it is arguably just as critical to the next decade of space industrialization. By turning the most dangerous phase of spaceflight, hypersonic atmospheric entry, into a manageable, scalable industrial process, C-PICA is doing for re-entry what the Falcon 9 did for launch, democratizing it. To understand why C-PICA is revolutionary, we must first appreciate the brutality of the problem it solves. Returning from low Earth orbit requires a spacecraft to shed orbital velocities of approximately 7.8 kilometers per second. That is about 17,500 miles per hour. When a capsule hits the atmosphere at that speed, it is compressing the air ahead of it so violently that the gas molecules cannot get out of the way. They are crushed into a shockwave, where temperatures can soar above 500 degrees Celsius. That is hot enough to vaporize steel. For the first half-century of spaceflight, solving this heat problem was the domain of superpowers. The solutions were heavy, complex, and ruinously expensive. The Apollo capsules used a material called AVCOAT, which was an epoxy novolac resin injected into a fiberglass honeycomb. It was effective, but manufacturing it was an agonizingly manual process. Gun-wielding technicians had to inject the material into hundreds of thousands of individual honeycomb cells, and the resulting shield was heavy and difficult to scale. The Space Shuttle took a different approach with its reusable silica tiles and reinforced carbon-carbon panels. While reusable, these systems were fragile, complex to maintain, and notoriously unforgiving of damage, a lesson learned in the most tragic way possible with the loss of Columbia. Then came PICA. Developed in the 1990s at NASA Ames Research Center, Phenolic Impregnated Carbon Ablator was a quantum leap forward. It was a low-density ablative material, meaning it was designed to burn away. As the heat of re-entry attacked the shield, the PICA would char, and pyrolysis gases would flow out to form a cool boundary layer, carrying the heat away with the shedding material. PICA was lighter than AVCOAT and could withstand higher heat fluxes, making it capable of surviving the blistering speeds of a return from Mars or an asteroid. It famously protected the Stardust capsule in 2006, which hit the atmosphere at a record-breaking 12.9 kilometers per second. But legacy PICA had a fatal flaw for the commercial era. It was hard to make. The backbone of traditional PICA is a material called fiberform, a rigid, block-like carbon preform originally designed as insulation for high-temperature vacuum furnaces. Manufacturing a heat shield out of fiberform is a subtractive process. You have to buy large, expensive billets of this rigid material, machine them into precise tiles, and then painstakingly assemble them into a mosaic on the spacecraft's aerosol. It is like tiling a bathroom floor, if the tiles cost thousands of dollars each and a single gap meant the destruction of the house. Because fiberform is rigid and brittle, you cannot just wrap it around a curved surface. You are forced to use a tiled approach for anything larger than a very small probe. This introduces gap fillers, materials needed to seal the spaces between tiles, which adds complexity, failure points, and labor hours. For a company like SpaceX, which uses a proprietary version of PICA called PICA-X for its Dragon capsules, or for NASA's Mars missions, this complexity is manageable. But for a startup wanting to bring back a small capsule of pharmaceuticals every month, it was a bottleneck. This is where the genius of C-PICA lies. It did not just improve the material, it changed the form factor entirely. Conformal is an engineering term that sounds dry but implies magic. In the context of C-PICA, it means flexible. Instead of starting with a rigid block of fiberform, C-PICA starts with a rayon-based carbon felt, a soft, compliant textile that looks and feels a bit like a high-tech blanket. This shift from rigid block to flexible felt changes everything about the manufacturing process. First, it brings about the end of tiling. Because the underlying carbon matrix is flexible, it can be shaped. A single large sheet of C-PICA precursor can be molded over the curve of a heat shield substructure. This allows for the creation of large, monolithic heat shields, without the need for hundreds of individual tiles. For a vehicle the size of Varda's W-series capsules, which are roughly 1 meter in diameter, a C-PICA shield can be manufactured as a single, seamless unit. This eliminates the need for gap fillers, reduces the aerodynamic trip hazards that can cause uneven heating, and dramatically simplifies the assembly process. Second, it ensures supply chain resilience. The rigid fiber form used in legacy PICA is a niche product with a limited supply chain. Carbon felt, on the other hand, is a more commoditized industrial material. By decoupling high-performance reentry from a boutique supply chain, NASA Ames and its commercial partners have made the material more accessible and less prone to shortages. Third, we have mass and cost efficiency. C-PICA is not just easier to use, it is better. It offers a mass savings of approximately 50% compared to traditional PICA for the same thermal protection capability. In the tyranny of the rocket equation, where every gram counts, saving half the mass of your heat shield is a monumental victory. It means more payload capacity for the pharmaceuticals, fiber optics, or semiconductors being manufactured in orbit. Furthermore, because it reduces the touch labor required for machining and assembly, the cost per unit drops significantly. Varda produces its C-PICA shields in-house at their El Segundo facility, a feat that would have been nearly impossible for a startup using the old AVCOAT or tiled PICA methods. The success of yesterday's W-5 landing is the ultimate validation of this felt revolution. It proves that you do not need a billion-dollar government program to build a hypersonic entry vehicle. You need a roll of carbon felt, some phenolic resin, and the engineering daring to embrace a new paradigm. While NASA Ames developed the technology, it is the commercial sector that is actively weaponizing it to build a business. Two companies in particular stand out as the primary beneficiaries and drivers of the C-PICA ecosystem: Varda Space Industries and Inversion Space. Varda is the poster child for the space factory concept, founded by former SpaceX engineer Will Brewy and Founders Fund principal Dilian Asparahov. Varda's thesis is simple: gravity is a manufacturing variable. On Earth, gravity causes sedimentation, convection, and buoyancy, forces that interfere with the formation of perfect crystal structures. By manufacturing in microgravity, Varda can create pharmaceutical crystals that are purer, more uniform, and more effective than anything made on the ground. But Varda is not just a pharma company, it is a re-entry company. As Asparahov has famously quipped, they are effectively a drug delivery company in the most literal sense. The W-series capsules are their delivery trucks. For Varda, C-PICA is the enabler of their business model. Their goal is a high cadence of missions, eventually reaching monthly launches and landings. To achieve this, they need a heat shield that can be mass-produced on an assembly line, not crafted by artisans. The W-5 mission marks the transition from experimental prototype to production hardware. While Varda focuses on manufacturing, Inversion Space is focused on logistics. Their vision is space as a shortcut. They aim to use orbital capsules to deliver cargo anywhere on Earth in under an hour. It is a concept that the military has dreamed of for decades, but Inversion is approaching it with a commercial mindset. Their Ray and Arc vehicles are designed to store cargo in orbit and deploy it on demand to precise locations on Earth. For them, C-PICA is equally critical. A logistics vehicle needs to be cheap and robust. If you are delivering medical supplies to a disaster zone, you cannot afford a heat shield that costs millions. Inversion has worked closely with NASA Ames to adapt C-PICA for their specific flight profiles, which involve high-G, precision landings. The collaboration between these startups and NASA is a textbook example of successful technology transfer. NASA developed the fundamental material science, and companies like Varda and Inversion are taking it through the valley of death to commercial operations. The landing of W-5 offers a prime opportunity to reassess the economics of the low Earth orbit economy. Market analysts project the in-space manufacturing market to grow from roughly $1.2 billion in 2025 to over $1.5 billion by the end of 2026. Historically, the space economy was a one-way street. We sent satellites up, and they stayed there until they burned up or became junk. C-PICA turns the street into a two-way highway. By reducing the cost of the heat shield, one of the most expensive subsystems of a re-entry vehicle, C-PICA lowers the overall mission cost. Varda has targeted a cost per flight of roughly $2.5 million once they reach maturity. If a capsule can carry 100 kilograms of payload, the cost of return drops to $25,000 per kilogram. While still high compared to air freight, this is orders of magnitude cheaper than previous sample return missions. The democratization comes from speed as much as cost. A flexible felt-based manufacturing process allows for rapid curing and molding. Varda does not need to wait months for a supplier to machine a billet of fiber form. They can impregnate and mold a shield in days. This supports their goal of a monthly cadence. Let's take a technical deep dive into why this felt matters. To truly appreciate the C-PICA shield, we need to zoom in to the microscopic level. Standard PICA is a composite of a carbon fiber preform and a phenolic resin. The fiber form provides the structural skeleton, while the phenolic resin provides the ablative mass. The key to PICA's performance is its high porosity. It is mostly empty space. This makes it an incredible insulator. However, the carbon fibers in fiber form are arranged in a specific, rigid orientation. This gives it anisotropic properties. It is stronger in one direction than another. C-PICA uses a carbon felt. Felt is a non-woven textile where fibers are matted together randomly. This gives the material a few distinct advantages. First, isotropy. The random orientation of fibers makes the material's properties more uniform in the plane of the felt. This simplifies the thermal modeling. Engineers do not have to worry as much about the grain of the material. Second, strain compliance. This is the big one. Rigid materials crack when they expand or contract at different rates than the structure they are glued to. This is why the space shuttle tiles had to be separated by gaps. C-PICA is compliant, meaning it has a bit of give. It can stretch and compress slightly without cracking. This allows it to be bonded directly to the aluminum or composite structure of the capsule without complex strain isolation pads. It moves with the vehicle, not against it. The W-5 capsule's survival was a test of this compliance. As it slammed into the atmosphere, the vehicle structure likely flexed and heated up. A rigid shield might have cracked. The C-PICA shield, acting like a flexible charred skin, absorbed the punishment and held firm. While the immediate commercial application is bringing drugs back from LEO, the lineage of C-PICA points toward the Red Planet. NASA's original interest in PICA was for high-speed entries. The Stardust mission proved PICA's worth at 12.9 kilometers per second. C-PICA retains these high-performance thermal characteristics. As we look toward future Mars sample return missions, or even human landings, C-PICA offers a compelling solution for the backshell of these vehicles. Currently, Mars landers use tiled PICA or other heavier materials for their backshells. Switching to C-PICA could save hundreds of kilograms of mass. On a Mars mission, where the gear ratio, the amount of fuel needed to launch payload, is huge, saving 100 kilograms on the entry vehicle might save thousands of kilograms of launch fuel. Furthermore, the conformal nature of the material opens up new vehicle shapes. We are no longer limited to the classic blunt body capsule shapes of Apollo. C-PICA could enable slender, lifting body designs or complex geometries that offer better aerodynamic control during descent. As we stand in January 2026, the successful return of W-5 is just the opening salvo. We will likely see C-PICA become the standard for small to medium-sized re-entry vehicles. Companies may emerge that sell re-entry kits, pre-manufactured C-PICA nose cones and heat shields that can be bolted onto standard satellite buses. This would allow university CubeSat teams or small nations to conduct sample return missions without needing to develop their own thermal protection materials. The current limitation of C-PICA is size. While you can make a 1-meter shield in one piece, making a 5-meter shield for a Starship-class vehicle or a large human capsule would still require seaming multiple sheets of felt together. Developing reliable seaming techniques for C-PICA is the next engineering frontier. If solved, we could see massive C-PICA shields protecting commercial space stations or heavy-lift cargo landers. Space exploration is often defined by its loudest moments: the roar of the rocket, the cheer of the control room, the sonic boom of the return. But often, progress is defined by the quiet revolution of materials science. It is the story of how a lighter alloy allowed for a bigger engine, or how a better battery enabled a longer rover drive. The C-PICA shield is one of these quiet revolutions. It is a piece of black, fuzzy carbon felt that has solved a problem that bedeviled engineers for 60 years. It has taken the art of heat shield manufacturing and turned it into a process. By lowering the barrier to entry for re-entry, C-PICA has effectively completed the circuit of the space economy. We now have a scalable way up, with rockets like Falcon 9 and Electron, and a scalable way down with C-PICA capsules. The loop is closed. As Varda's technicians in Australia begin the process of dismantling the W-5 capsule to retrieve their crystal payload, they are not just unloading cargo, they are unpacking the future. A future where made in space is not a novelty stamped on a souvenir, but a standard origin label on the medicines that save our lives and the chips that power our computers. The door to the Orbital factory is open, and C-PICA is the doormat. Thanks for listening to G Fun Facts Online.